Dr. D here, and today we're going to learn Le Chateliers Principle and see what happens if you have a system at equilibrium and then add more reactants to it. So let's dive into it in Content with Content. So Le Chateliers Principle states, if a change is imposed on a system at equilibrium, the equilibrium will shift so as to reduce the change. And we're going to go through a couple of examples here and see what this really means. So to begin with, let's say we have a vessel filled with some gases, and they're at equilibrium according to the equation shown here, where we have nitrogen gas, N2, plus 3 hydrogen gas, H2, and 2 ammonia, NH3. We can figure out the equilibrium constant with the equation shown here. And let's say we impose a change. Let's say we add more of one of the reactants. Let's say we add more N2. Well, this will change our reaction quotient so that our concentration of N2 has gone up. So that means our denominator has increased, meaning that Q is going to be a smaller number. So since K is greater than Q, this means that the reaction is going to shift to the right to make more products to counterbalance this extra influx of the reactants. And so this will ultimately cause our concentrations to change from the original scenario when we were at equilibrium. So our concentration of N2 is going to go up because we added more N2. Our concentration of H2 is going to go down because of the shift. And then our concentration of NH3 is going to go up because of the shift. Let's take a look at another scenario. Let's say we have our system at equilibrium, but this time we're going to add more products. So we're going to add more NH3. As we do this, our numerator is going to increase, meaning that now K is less than Q, and this will cause the reaction to shift to the left to make more reactants. And so it's going to affect our concentrations ultimately in that N2 is going to increase because of the shift. Our concentration of H2 is going to increase because of the shift. And then, in truth, our concentration of NH3 has increased because we added a lot more NH3. Let's take another scenario. Let's say we are going to remove some of our product. And we could do this by adding something that reacts with our product. In this case, we could add in some HCl, and that will cause it to precipitate out. So let's say we add some HCl, we lose some of our NH3, and now our reaction quotient is going to change in the fact that our numerator is now smaller. So this is going to mean that Q is going to be a smaller number. So now K is greater than Q, and this is going to cause our reaction to shift to the right to make more products to counterbalance the loss of the products previously. And so how's this going to affect our concentrations? Well, our concentration of N2 is going to go down because of the shift. Our concentration of H2 is going to go down due to the shift. And then our concentration of NH3 still goes down because we reacted some of it. So since we lost some, it's still going to be down from our original amount. All right, let's take a look at another scenario. Let's say we have our gases here. We put in a slightly different vessel this time because we're going to increase the volume. So when we remove the valve, we double the volume, and our gases are going to spread out to occupy that space. Now, since there's more space here, we're going to be looking at these as the gases. So we start off with 4 moles of gas in our reactants, 1 from N2, 3 from H2, and 2 moles of gas in our products from the NH3. Well, since we're increasing the volume, we are going to be shifting to the side with the gas that takes up more volume. So 4 moles of gas takes up more volume than 2 moles of gas. And so in this case, the reaction is going to shift to the left to help occupy that extra space. So this is going to ultimately cause all of our concentrations to go down because we've increased the volume. It is an inverse relationship to concentration. So since concentration is moles per liter, we increase the volume, so all the concentrations are going to go down. Now, this is going to be less so for our N2 and H2 because of the shift, but they will still all go down. All right, let's take a look at one more scenario. So we have our reaction here, and the enthalpy of this reaction is negative 105 kilojoules per mole. Now this negative sign means that we're releasing heat to the environment. All right, so this is considered to be an exothermic reaction. And one way to kind of look at this in a slightly different way is we can put heat as a product. All right, so in truth, we're changing the equilibrium constant because we're changing the temperature. But if we think of heat as a product, we can still apply what we've learned with Le Chatelier's principle. So in this case where we have an exothermic reaction, if we increase the temperature, it's like we're increasing the amount of product. And so that's going to cause a shift to help minimize that change. And so we're going to shift to the left and make more reactants. If we decrease the temperature, then it's like we're removing one of our products. And so that's going to cause the shift to go to the right to make more products. Now, another scenario you might come across is you might have an endothermic reaction, and essentially it's the reverse. In this case, it would be that heat would be like one of the reactants. And so if we increase the temperature, it's like we're increasing the number of reactants, and so that'll cause a shift to the right to make more product. If we lower the temperature, it's like we're removing some of the reactants, and so we're going to cause a shift to the left and make more reactants. So that's all I have for you today. I hope you have a better understanding of Le Chatelier's principle of how things shift to minimize the change. So, as always, keep thinking, and I'll see you next time. Goodbye!